Energy efficiency in building construction, the Iecc code. So what is a HERS rating? HERS stands for Home Energy Rating System and is a national standard that uses information on the design of the energy systems in a home to calculate, via computer modeling, the average energy needs of that home and give it a rating score. Of course, you see HERS used, or it's demanded to be used in a few different areas. You might need it for a lead rating. Different cities and towns require it, so this is why we're going over this section. So how does a building official in a town or city check that if you've met the energy stretch code? And that's done by achieving a HERS rating or an Energy Star Home certification. And here you go right here. This is where the HERS is tied to at least one type of local or city code, and that's the stretch codes, because stretch codes are not usually statewide. They're usually being required on a town-to-town or city-to-city basis. So here we'll take a look at comparing HERS to prescriptive. There is an approach called the prescriptive approach. A lot of times you're given both options. So choosing to follow the HERS rating approach used by new construction often makes sense when doing a whole house renovation. While using the same HERS approach as new homes, existing homes have an easier standard to meet. Next, we'll take a look at the stretch code. And a stretch code is a locally mandated code or an alternative compliance path that is more aggressive than the base code, depending on the state, resulting in buildings that achieve higher energy savings. So how is the stretch code implemented and enforced? Pretty much the same as the regular building code within a state. So here are some of the items that are covered by the stretch code: basement walls, sunrooms, better air tightness requirements, air leakage control, air barriers, piping insulation, roofs, fenestration, and lighting. It's also good to mention that these will be looked at in the following section under changes in the Iecc code. And the Iecc, which is the International Energy Conservation Code. It is a model code adopted by many states and municipal governments. It's becoming a ubiquitous type code requirement that is going through the United States and pretty much filtering into every state. According to the Iecc, only a handful of states have implemented the 2012 Iecc code as of October 2013. Here we'll leave behind the stretch code and segue into the residential provisions of the 2012 Iecc code. And of course, probably most helpful to look at the changes that have been made to the residential provisions of the 2012 Iecc code. And here's a summary of the changes that have been made to the Iecc code, and this is the 2012 version is considered to be 30% better than the 2006 Iecc. They've also consolidated with IRC the energy chapter. Of course, the IRC code is covered in the energy section of the continuing education presentations. It's mandatory, and a whole house pressure test is another major change here, and along with more stringent duct leakage tests and some DHW distribution system requirements. And in this review of the 2012 Iecc code change, we'll do an overview of the major changes along with minor changes and some of the key non-changes, which gives you a good idea of things that are staying in place and have already been a base for the code. And we'll look at the lighting requirements, which are now made to be mandatory, and some envelope equipment trade-offs. And in the section that contains the residential code, we have Chapter 1 is Scope and Application, Administrative Enforcement, pretty much the same as the Commercial Code, Definitions. In Chapter 2, Chapter 3, General Requirements. Chapter 4, Residential Energy Efficiency. That we'll take a good look at, and that pretty much is in line with this presentation on energy efficiency. And Chapter 5, the Referenced Standards. So here's a chart that pretty much sums up all of the changes and things we'll be looking at in the Iecc code. And we find that fenestration is one thing. We'll be looking at that last here in the presentation. But at the very end of the chart is wood frame walls. That'll be coming up next. R values, and working backwards here, ceiling and R values are important. The glazing fenestration, the solar heat gain coefficient, and the skylight U factor. Of course, these rules change, and if you noticed in that previous chart, they're all dependent on what climate zone you're in. And here are the different climate zones, and each climate zone will have their own different requirements. You'll see that mentioned throughout the presentation. So let's take a look at walls first. And here are some of the provisions of walls using the U factors for the climate zones. Next, about basement walls, below or under 50% below grade. Otherwise, they're treated as an above grade wall. This is the amount of insulation that you need, depending on the height of the grade. And here are the corresponding R values to the climate zone areas. Next, we could take a look at the steel wall frame section. And moving up from the basement to wall sections, here's a handy chart for steel framed walls. The requirements are our requirements and values of insulation. Also on the right is a bit for the truss ceilings and the joist ceilings. Of course, the 24-inch on-center spacing is not relevant to the exterior walls in Massachusetts. And of course there are exceptions, one being sunrooms. In general they have less stringent insulation requirements, along with the R value and glazing U factor requirements. And a sunroom is defined as a one-story structure with a glazing area of less than 40% of gross exterior wall and roof area. Has separate heating or cooling system or zone. And of course it must be thermally isolated, closable doors or windows to the rest of the house. Those are generally defined as exterior doors or windows, and can always meet table R402.1.1 requirements with unlimited. And we'll take a look at the next slide here. And of course there are exceptions, one being sunrooms. In general they have less stringent insulation requirements, along with the R value and glazing U factor requirements. And a sunroom is defined as a one-story structure with a glazing area of less than 40% of gross exterior wall and roof area. Has separate heating or cooling system or zone. And of course it must be thermally isolated, closable doors or windows to the rest of the house. Those are generally defined as exterior doors or windows and can always meet table R402.1.1 requirements with unlimited. And we'll take a look at the next slide here. And here are some of those less stringent requirements for the different zones, but always bearing in mind that local code and whether it be local localities type codes that are used in the stretch code or the overall mass code would definitely trump any of these requirements. But in general, for zones 5 through 8, which Massachusetts is within, would be R24 for the wall insulation, and the fenestration factor would be 0.45 for windows and the wall windows or wall treatments, and the skylight would be a U factor of 0.70. Just another handy little bit of a chart here, something to work on, a good base. So let's take a look at the next section, which is the air leakage control idea. The Iecc code is very intensive in this area and covers most of the building envelope and different types of penetrations and areas where cracks and crevices where cold can get in and warm can also escape. In 2009, the international codes included provisions to improve air tightness of new homes. Prior to 2009, builders were given two compliance options: either follow a checklist of measures or have the home tested with a blower door. The new 2012 code doesn't give builders a choice anymore. Builders now have to comply with both the checklist requirements and the requirement to conduct a blower door test. The air sealing checklist in the 2012 Iecc is called Air Barrier and Insulation Installation. All items on the checklist must be followed. The 2012 code provides some leeway. And some of the ways that you can comply with the air barrier requirements, I think this is pretty much stating the obvious, but through materials or assemblies or in the building process. Basically, a continuous air barrier shall be installed in the building envelope. Starting with air barrier, the requirements here, of course, and a little bit of an exception there in climate zones 1 through 3, but in our areas, the air barrier requirements are placement allowed inside of the building envelope or outside of the building envelope, mostly located within assemblies composing envelope or any combination thereof. So continuous for all assemblies, part of the thermal envelope, and across joints and assemblies. We see a little bit more of an idea here with the joints and seams to be sealed, and of course that leads you to another regulation, another bit of the code, so that can be looked up also. And where similar objects are installed that penetrate the air barrier, make provisions to maintain the air barrier's integrity. Well, I'm trying to think of a maybe a some sort of example here. Possibly a shaft or some item that, like the air return that goes to the air conditioners, or a chase or something of the sort that goes up to the roof would be one example. Breaks and joints in the air barrier need to be sealed. The table requires that the air barrier and any drop ceiling or soffit shall be aligned with the insulation, and any gaps in the insulation or air barrier sealed. Along with that, corners and headers shall be insulated, and the junction of the top plate and the top of the exterior walls shall be sealed. Knee walls also shall be sealed. Exterior thermal envelope insulation for frame walls shall be installed in substantial contact and continuous alignment with the air barrier. The spaces between windows and door jambs are also looked at, as well as rim joists. Insulation shall be installed to maintain permanent contact with the underside of subfloor decking. Where provided in lieu of floor insulation, insulation shall be permanently attached to the crawl space walls. And a little bit about the exposed earth and unvented crawl space walls. Duct shafts, utility penetrations, and flue shaft openings to exterior or unconditioned spaces shall be sealed. Vats and narrow cavities shall be cut to fit. Air sealing shall be provided between the garage and conditioned spaces. Recessed light fixtures shall be insulated. Mat insulation needs to be neatly cut and fit around wiring and plumbing. Exterior walls adjacent to showers and tubs shall be insulated. The air barrier shall be installed behind electrical or communication boxes. HVAC registers and boots that penetrate the building thermal envelope shall be sealed to the subfloor or drywall. An air barrier shall be installed on fireplace walls. Fireplaces shall have gasketed doors. Climate zones 1 through 3. Air barrier requirements. Continuous for all assemblies, part of the thermal envelope, and across joints and assemblies. Next, we'll take a look at some items on air leakage. Here we'll take a look at some of the air exchange rates, leakage rates per climate zone. And here we'll look at duct tightness testing. The code permits builders to test a duct system in one of 3 ways. One option is the rough-in type. Another option is a so-called rough-in test after the air handler is installed. And a final third option is called post-construction test. And with all on the air infiltration, we'll take a look at the duct sealing. And found in the duct sealing section, R403.2.2. And of course sealing is mandatory. The reason for this is to keep the interior conditioned air separate from any air that would be found in the plenums or chases or other air spaces that the ductwork moves through. And just to say, what is the problem of duct leakage has often been shown through many studies that have been conducted throughout the country, and have found that poorly sealed ductwork is often the most prevalent and yet easily solved problem in new construction. And duct leakage does contribute to 10 to 30% of heating and cooling loads in many homes. That would be, of course, through the loss of air through different poorly sealed portions of duct, improperly engineered ductwork. And additionally, duct leakage can lessen comfort, which also endangers health and safety. So locating ducts in conditioned space eliminates many problems with leakage. They're often installed in chases, which can be problematic, and framed air passageways situated behind ceilings or wall finish are basically the same, have the same problems.
These chases are often connected more directly to unconditioned space rather than interior space, and so you have that mixing of two different types of areas between the what is not really the conditioned and air that should be of indoor air quality for the interior space. So therefore it is important to seal these areas completely from unconditioned spaces. And a common practice is sometimes putting the air handling unit in the garage. Supply and return air ducts are connected to the unit through the main supply duct and a return air plenum, but while this practice saves in interior space by locating the equipment in the garage, it can often cause problems. The garage is a storage area for gasoline, paint, solvents, insecticides, and other different chemicals. So never mind of course, the car with the carbon monoxide and waste products of combustion when you drive the car in, and or even keep it idling for a bit to warm it up in the morning. So any leaks in the return side of the air handling unit can draw these fumes into the air conditioning system, and this creates indoor air quality problems that could be serious. So the heating and cooling contractor should use proper materials when sealing duct work, in particular duct sealing mastic. And duct insulation does not provide an airtight seal. We just keeping that in mind. To ensure ducts are tight, have your HVAC contractor conduct a duct leakage test, and you can at least know where you stand, and this is an imperative. At least having a good idea of how well the ducts are working or how well they are not working.
And here are some of the duct sealing exceptions. We'll also take a look on the next slide at a few more. Again, the duct sealing exceptions. In general, forced air heating and cooling systems should be balanced. It's almost an imperative. The amount of air delivered through the supply ducts should be equal to that drawn through the return ducts. And if the two volumes are unequal, pressure imbalances may occur in the home, resulting in increased air leakage and possible health and safety problems. And if supply ducts in unconditioned areas have more leaks than return ducts, heated and cooled air will escape to the outside, increasing energy costs, for one. Less air volume will be supplied to the building, so the pressure inside the building may become negative. This is what causes air infiltration, and the negative pressure can actually backdraft flues at the very extreme end, which would pull exhaust gases back into the home from fireplaces and combustion appliances. These health effects can be deadly if flues contain substantial carbon monoxide. And with return ducts, if they happen to leak, the home can also become pressurized, which increases air leakage out of the envelope. Hot, humid air is often pulled into the system ducts in the summer, and cold air is drawn into the ducts in winter. We have human health problems, of course, of ducts that are located in areas where there are radon, mold, or toxic chemicals from soil termite treatments, paints, cleansers, and pesticides, for example. And of course we have the same problem that combustion appliances are located near return leaks. The negative pressure created by the leaks can be great enough to backdraft flues and chimneys. And in general, duct tightness tests are performed, and they should be verified by the following: in a post-construction test with the total leakage parameters given here, and basically all register boots taped or otherwise sealed. And second would be, of course, the first test you would have done would be the rough-in test, and giving the leakage amounts allowed here. Bearing in mind that pressure, it's a lot of the problem here is pressure imbalances that can cause air leakage, which also may draw additional moisture into the building. Proper duct design and installation helps prevent imbalances from occurring. And the rough-in test. Here are some exceptions. A little bit more about the blower door test. Every new home must pass a blower door test. It's up to the local code official to determine whether builders can conduct their own tests. And the code does not require third-party testers to have any type of certification. And here are some of the provisions of the Iecc code. This is a map of the different zones. A little bit more about blower door testing.
And moving to the testing of air barrier integrity is the testing through an air leakage rate. The air leakage rate is should be confirmed not to exceed 0.40 cubic feet per minute per feet squared at a pressure differential of 0.3 inches water gauge and per ASTM E779 or equivalent method approved by the code official.
And finally, a written report of the results shall be signed by the party conducting the test and provided to the code official. Next, we'll take a look at what is required for air handlers. And here are some of the requirements on the air handler. And basically, that air handlers have a manufacturer's designation for air leakage of 2% or less of design airflow. And we'll take a look at why building cavities cannot be used for ducts or plenums for much of the same reasons that we talked about with the duct air leakage. It causes the same problems as different airs and gases being drawn into the interior environment. And we'll move on to piping insulation and what is mandatory. And this is required, of course, R3 required on HVAC systems. They say with the Iecc code there's an exception, piping that conveys fluids between 55 and 105 degrees Fahrenheit. But if exposed to weather, obviously protect from damage, including sunlight, moisture, problems that occur during equipment maintenance, and wind problems. In general, provide shielding from solar radiation that can cause degradation of material. And keep in mind that adhesive tape is not allowed. And we'll move on to piping insulation and what is mandatory. And this is required, of course, R3 required on HVAC systems. They say with the Iecc code there's an exception, piping that conveys fluids between 55 and 105 degrees Fahrenheit. But if exposed to weather, obviously protect from damage, including sunlight, moisture, problems that occur during equipment maintenance, and wind problems. In general, provide shielding from solar radiation that can cause degradation of material. And keep in mind that adhesive tape is not allowed. Here we'll take a little look at the piping insulation and the requirements. R3 is required on piping less than 3/4 of an inch in nominal diameter and piping serving more than one dwelling unit, along with piping from the water heater to kitchen outlets. R3 is required on piping located outside the conditioned space, piping from the water heater to a distribution manifold, and piping under a floor slab. R3 is also required on buried piping, supply and return piping, and piping with run lengths greater maximum run lengths for nominal pipe diameter, as described in Table R403.4.2. And all remaining piping to be at least R3 or meet run length requirements in the aforementioned table. And outside air intakes and exhausts shall have automatic or gravity dampers that close when the ventilation system is not operating. The whole house mechanical ventilation system fans are to meet FSC in Table R403.5.1, with one exception, that when fans are integral to tested and listed HVAC equipment or powered by electronically commutated motors. And outside air intakes and exhausts shall have automatic or gravity dampers that close when the ventilation system is not operating. The whole house mechanical ventilation system fans are to meet FSC in Table R403.5.1, with one exception, that when fans are integral to tested and listed HVAC equipment or powered by electronically commutated motors. Here is another chart with that outlines mechanical ventilation with their airflow rate maximums, the minimum FSC, and the airflow rate minimums for range hoods, inline fans, bathroom, utility room usage. And here's a bit on the importance of equipment sizing. The reason for these load calculations and the second item, where the goal is big enough to ensure comfort but no bigger, are all revolve around that one of the most important decisions regarding a new building is the type of heating, ventilation, and air conditioning system to install. Equally critical is the heating and cooling contractor selected. The operating efficiency of a system relies on proper installation to achieve the performance rating. And some keys to obtaining the design efficiency of a system in the field include sizing the system for the specific heating and cooling load of the building being built, and bearing in mind that one size does not fit all. A proper load analysis needs to be performed for the HVAC system to operate in an efficient and predictable manner. This includes the selection and proper installation of thermostats and controls, and a ductwork system designed to deliver the correct amount of air-conditioned air to each space within the building. And of course, going back to what we mentioned before, the insulating and sealing of all ductwork. Improper installation of components, in particular ductwork, has a negative impact on comfort, increases energy bills, and can dramatically degrade the quality of air in a building. Poorly designed and installed ducts can create conditions that may reduce comfort, degrade indoor air quality, and even threaten the well-being of the occupants. The goal is to have equipment big enough to ensure comfort, but no bigger than is needed. Next, we'll take a look at some of the new requirements for pools and permanently in-ground spas. Here we'll move into some of the Iecc requirements for pools, in-ground permanently installed spas as well. And on heaters, they need to have a readily accessible on-off switch, which is mounted outside the heater, so the heater can be shut off without adjusting the thermostat. They need to be fired by natural gas and not allowed to have continuously burning pilot lights, time switches or other control methods to automatically turn off and on heaters and pumps according to a preset schedule should be installed on all heaters and pumps. And again, some rules on pools and in-ground permanently installed spas, that heater pumps and motors with built-in timers meet the requirement. There are some exceptions, and the public health standards requiring 24-hour pump operation, and pumps operating pools with solar waste heat recovery heating systems. And here are a few of the exceptions regarding pools and in-ground permanently installed spas.
And moving pretty much in the same format as the residential section before that we presented, we move into pools and spas, which for commercial buildings we find especially in hotels and any of these any type of maybe executive office buildings, it's not 100% common, but it is does occur. And again, we have that. This is exactly the same as for the residential requirements, and again, the cover must be vapor retardant, and you have one exception if you're using site recovered energy.
Here, regarding pools, we have some of the requirements on the covers, and in general, there is one exception, and if less than 70% of energy is from site recovered energy. Next, we'll take a look at some of the new requirements for lighting.
And continuing here with the lighting requirements, the interior lighting. Basically, in an overall sense, there are required controls in total. There are wattage and efficiency limits, and interior lighting power allowances, which are always figured by watts per square foot. Here are the for the exterior lighting controls are again required controls and lamp efficiency, and exterior lighting power allowances need to be calculated also, same as watts per square foot, and electric metering. And of course, all these should be either, and quite often are separately metered with, let's say, strip malls, so on and so forth, where where it's part of the overall common charges that are used for the building. But at any rate, there's a lot of requirement here on metering, and as it's always has been said, if you can't measure what you don't meter. So the metering gives a good rule of thumb of waste in a certain area, and so on and so forth. And here are some of the caveats for retail and warehouse type lighting applications. And in general here, no additional lighting allowed for retail lighting, but daylighting controls option for retail and office lighting, and 70% of daylit floor area for warehouse occupancies.
Lighting in high efficacy lamps. The Iecc requires that a minimum of 75% of the lamps in permanently installed lighting fixtures shall be high efficacy lamps. The code defines a high efficacy lamp as either a compact fluorescent light, CFL, or a T8 or smaller linear fluorescent lamp, or any lamp meeting the minimal efficiency requirements. A minimum of 75% of the lamps in permanently installed fixtures shall be high efficacy lamps, or 75% of permanently installed lighting fixtures to contain only high efficacy lamps, with one exception: low voltage lighting. Here are some of the CFL lighting requirements. And next, where to post all your certifications. And finally, in closing, when upon receiving a certificate, you have some requirements here that it should be permanently posted on or in the electrical distribution panel. Don't cover it or obstruct the visibility of other required labels. I think that goes without saying, but includes the following on the label: the R values of insulation installed for the thermal building envelope, including ducts and outside conditioned spaces. It includes the U factors for fenestration. It includes the SHGC for fenestration. And it has the results from any required duct system and building envelope air leakage testing. Also includes HVAC efficiencies and types and the SWH equipment. Next, we'll take a look at a concept called SHGC, the solar heat gain coefficient. Now, true that it's not used so much in the calculations and charts that you see for the residential section, it's still a term to be familiar with.
And here is a better explanation of the SHGC. It is the amount of solar radiation that can pass through a window or skylight and can be measured in terms of its solar heat gain coefficient. A little bit more information can be found at this link down below. If anybody cares to take a little bit of a further look at SHGC and what the ratings are, I have a little bit more information here on the next slide.
So SHGC ratings are used to help in quantifying the energy efficiency of windows and skylights, kind of like R value for insulation and walls.
And this gives a little bit better information or understanding of what the numbers mean with the SHGC. And the SHGC is best described as a ratio where 1 equals the maximum amount of solar heat allowed through a window, and 0 equals the least amount possible allowed through. So, and a rating of 0.30 means that 30% of the available solar heat can pass through the window. And of course, a handy way to figure that out is any whatever point number it is, 0.50 would be 50%, so on and so forth. Just to give it a bit of translation into percentage terms. A little bit more on the certificate. It lists if gas-fired unvented room heater or electric furnace or baseboard electric heater, rather than listing any efficiency for those heating types. So that's pretty general, and that concludes our presentation on the certificate requirements and other requirements in general for the Iecc code and the energy efficient building construction. And starting with roof insulation, we can take a look at how the roof insulation is calculated and estimated, what categories it's broken down to. Here we see the roof R values and U factor requirements. Just to say that in the eastern part of the United States, it's mostly the R value, of course, that is keyed on here. And the three different categories are whether or not the insulation is entirely above the deck, and if they are metal buildings, that creates another category, and the third category is attic and other types of installations for insulation. But first we can take a look at another technology altogether, and that's cool roofs and some of the different idiosyncrasies about cool roofs. So this area pretty much keys in on the idea that the roofs are a pitch of 212 or equal to or less than, And these roofs can obviously qualify for one of 4 minimum roof reflectance and emittance options, depending on the some of the properties of these of the different materials used. We'll take a look at that in a minute. And as always, there are exceptions. In this area, we have what are called high albedo roofs, and some of the exceptions. The exceptions are, of course, if portions of the roof that include or are covered by PV systems or components, solar air or water heating systems or components, roof gardens or landscaped roofs, which that brings into another thing into play altogether. They have their different R values, and these sustainable roofs are a good way of creating insulation for the entire building envelope. But moving along, we have the above roof decks or hallways, skylights, which is pretty obvious. The HVAC systems, wherever they're mounted, and certain portions of the roof that are shaded due to sun angles. Some roofs have these the ballasted stone on top. We see that a lot in the commercial applications. And then roofs where a minimum of 75% of the roof area meets one of the above exceptions.
More high albedo roof exceptions.
And moving into the requirements on fenestration, the vertical fenestration requirement is outlined here as being calculated as a percentage of vertical fenestration area to gross wall area, and that is allowed up to a 30% maximum of above grade walls. We have a little bit different category for climate zones 1-6. We'll be looking at a chart of the climate zones in a moment, and here it is up to 40% maximum, and that's what we'd key on in this area of Massachusetts, in total all of Massachusetts. And to break this down a little further, you would look for the requirements again by climate zone. Here the U factor table would be used again for finding requirements for your windows and fenestration. This gives an idea of one of the tables that can be found within the book, this one on insulation and fenestration requirements by component. What's good is you have the R values listed, and the U factors for windows, basically fenestration, skylights, and glazed fenestration. Pretty handy, makes it very simple to look up. Of course, the climate zones on the far left-hand side of the chart. Pretty much we're in we know the area that we're in is 5 and 4, 6. You have to look up in Massachusetts exactly what climate zone you're in your particular community or the place where you're doing building. The same chart can be used across the United States, which is good, and for any of the surrounding states. The requirements are pretty much the same in many states, so this becomes handy in that way, that it's an all-around encompassing type chart that would help you in any area. In the next section, we'll be talking a bit about how in passive design buildings, how passive heating and cooling due to windows and fenestration makes a significant difference, since a great amount of the heat, ventilation, and light for a house are provided also by windows. And we'll take a look at some of the details that are covered here in the next few slides. So here again is a little bit expanded version of the same idea with the vertical fenestration. And the thing to note here is the second item is that no less than 50% of the conditioned floor area is within the daylight zone. Well, that basically means, if the sunlight's falling on more than 50% of the floor space in the daylight zone, the idea, of course, is that that there's a lot of passive heating that happens this way of the floor, which then, of course, heats the interior environment. So automatic daylighting controls are installed in daylight zones, and it says the vertical fenestration is greater than or equal to 1.1 times the SHGC, and of course an exception. Yeah. And here is a little bit exactly on the skylight minimum fenestration. We're limited to 3% or less than the total roof area, but with the up to 5% allowed if, again, daylighting controls are used and installed in daylight zones. And skylights above daylight zones with automated daylight controls are permitted a maximum U factor, and the factors here, of course, that relate to us are the 0.7 factor in climate zones 4 through 8. This regulation here gets to be a little bit confusing, but the minimum skylight fenestration, which I think runs in opposition to what we discussed a few slides back, but that in certain types of enclosed spaces greater than 10,000 square feet and directly under a roof with ceiling heights of less than 15 feet, the total daylight zone under skylights is to not be less than half the floor area, and to provide a minimum skylight area to daylight a zone of either a minimum of 3% of roof area or provide a minimum skylight effective aperture of 1%. And here down below again we have some exceptions. And here we have some fenestration SHGC requirements. The SH, or solar heat gain coefficient, here are the effects of overhangs on fenestration are calculated. And overhangs allow a higher solar heat gain coefficient product to be installed. I don't see a lot of the parameters given here, but there are calculations that can be made. This probably begs a little bit more looking into. I would assume that the architect or building designer would have these requirements down. Of course, it's always good to check, so this is one of those areas that can be looked into a little bit more.
So in review, to cover it all, we can say that it is air barriers is one section that has been covered and looked at as far as better insulation. The idea of fenestration, air leakage, is being reduced through windows and doors. Air intakes, exhaust openings, and stairways and shafts are all need to be better insulated against air infiltration. One thing here for commercial is loading dock weather seals, vestibules, and for all recessed lighting. And now we'll take a look at HVAC, just a few more slides.
Here are some of the heating, ventilation, and air conditioning load calculations. They're mandatory also, following the ASHRAE standard of 183. And there are other approved computation procedures. Those are available in Chapter 3 of the guide of the code book. Here we have taken into consideration are the exterior design conditions, which are also specified by ASHRAE, and the interior design conditions, which are specified by the Iecc. In general, they're less than or equal to 72 of the heating load or 75 of the cooling load.
Here are some of the HVAC load calculations and who specifies them, both ASHRAE and the Iecc. And the all-important HVAC commissioning, it applies to buildings with a total building equipment capacity greater than or equal to 480,000 BTU in cooling capacity or 600,000 BTU in heating capacity. So what needs to be done under the commissioning plan? And that's systems adjusting and balancing, functional performance testing, equipment testing, controls testing, economizers testing that generates a preliminary commissioning report. Also, you have to tender construction documents and O&M manuals, and final commissioning report and air balancing report. And that concludes the presentation. Thanks for participating.